So in this lesson, we're going to look at another example of how we identify those conjugate acid-base pairs by determining what is a Bronsted-Lowry acid or base. So this is looking at the same reaction that we looked at in the previous lesson, just in a different format. So remember what we saw there was NH3 went to NH4 plus. NH3 is acting as a proton acceptor, and so that makes it a base. NH4 plus, when we looked at going in the opposite direction, will be acting as a proton donor, making it an acid. When I look at my H2O, again, I've got to find the partner that changes by one H plus. Those are our conjugate acid-base pairs. H2O to OH minus. I'm going to a proton donor, so that makes that an acid. And when I look at OH minus, going back to H2O, it's accepting a proton, making it a base. So we have two conjugate acid-base pairs here. We have NH3 and NH4 plus, make one conjugate acid-base pair, and then H2O and OH minus make another conjugate acid-base pair. Now you look at these, whenever we're assigning these, it's always within the context of a chemical equation. So which substances, because remember we're going to have two, act as an acid in the reaction? So when we look at this, we want to find our conjugate acid-base pairs first. So we say we've got an HF going to F minus because they differ by a single proton. And we're going to look at H2O and H3O plus. So those are our conjugate acid-base pairs. And then we want to say, well, which substances are acting as an acid? So which substances are acting as a proton donor? So which things are giving up a proton? So when I look from HF to F minus, I know that HF is giving up a proton because it's losing that proton as I go from HF to F minus. So I know HF will be an acid. When I look at water and H2O and H3O plus, I see that I'm gaining, going from H2O to H3O plus, I'm gaining a proton, which means the reverse process will mean that the H3O plus is the acid because it is willing to donate a proton. So what my answer here is my HF and my H3O plus. HF is an acid, H2O is willing to accept a proton, making it a base. And likewise, when I look at my F minus, it's willing to accept a proton, so it's also going to be a base. Notice I have an acid and a base on the left and an acid and a base on the right. I can never have an acid-acid conjugate pair or a base-base. I always have to have one acid and one base. One will be on the left side and one will be on the right side. I do want to show you one reaction with acids and bases, which is a neutralization reaction. And this is a reaction between an acid and a base, and it always generates a salt and water. And so remember, salt, in this case, for one example we see here, NaCl, we're talking about table salt, but a salt is basically any ionic compound. So a salt is a very generic class of compounds. So when we see this, we see HCl and NaOH, so we have a strong acid and a strong base, and they're producing NaCl and H2O. You will not need to predict the products of the reaction, but I just want you to know this basic idea of the salt and water. If I'm using hydrochloric acid in a lab, I'm probably going to keep some base, usually like baking soda, which is also a base, around so that if I spilled HCl, I could pour some baking soda on it. It would neutralize the acid, and so instead of cleaning up a strong or concentrated acid, now I'm going to be cleaning up a salt and water, which is a much easier mess to clean up. So this is our usual typical example. We see the first one, but we can also see this between any acid-base pair. Notice that we have HNO3 and BaOH2. We end up with BaNO3 and water. Again, you do not need to predict the products of the reaction.